evening, sir.
Yeah, good evening, madam. Yeah.
Sir, shall we start, sir?
Yes, madam. Yeah, we can start.
Yes, sir. Good evening to one person here. It's my great pleasure to welcome you all for this 6 days online ATAL FDP program on foundations and applications in quantum computing from qubits to quantum entanglement. Sir, this might be our third day. We are getting a resource person, a well-wished resource person from Dr. Anantharaman, Scientific Officer E rank, High Performance Computing Division Computer Center, National Institute of Science, Education and Research, NISER, Bhubaneswar. He is a highly skilled and experienced in high performance computing engineer, researcher, and educator with over the 14 years of expertise in HPC. Also, well in computer networks, network security, computer architecture, operating systems. His specialization is design, implementation, and management of advanced computing infrastructures that power cutting edge scientific research. He has played a pivotal role in building, operating, and maintaining the HPC clusters in Tier 2 organizations, Tier 2 data centers, providing a critical computational support for national level research at premier institutes. His notable contribution include the management of large-scale HPC systems at JNCASR, Bangalore and NISER, Bhubaneswar. Dr. Anandaraman is highly expertise in designed, implemented and maintained HPC clusters and Tier 2 data centers. Expertise in clusters, software stack management, SL, URM, job scheduling, parallel file system, and scientific software developments. His strong experience in Linux system administration, InfiniBand, networking, and cybersecurity for research infrastructure. With this, I wholeheartedly welcome our auspicious, prestigious resource person, Dr. Anandaraman, to take over the session.
Thank you. Thank you for nice introduction. Yeah. So I'm basically from Tamil Nadu only. Yeah. Shall we start, madam?
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Yes, sir. So now you open your screen.
Is it my screen visible, madam?
Yes, sir.
Okay.
Sir, can you maximize the screen, sir, if possible?
Yeah, yeah. Okay.
Yes, sir. Yes. It is
Okay.
visible, sir?
Yeah. Okay.
Yes, sir. Let us start.
Okay. 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 So good evening for all. So today we will discuss the topic of quantum algorithm. So just we will introduce to quantum algorithm. Okay. So what is the what is the advantage of quantum algorithm over classical algorithm? Why we are going for quantum algorithm and some mathematics behind that. Okay. We will discuss those things. Okay. So why quantum algorithm? So because we have classical computers, so our classical algorithms works. Okay. So because of Moore's law, is now no more valid. Okay. Moore's law states that for every 18 months, the number of transistor in the chip will get doubled. So that after 18 months, you will get the better CPU in the same cost. Okay. But that no longer sustained because the transistor size day by day it is getting smaller and the classical physics won't work actually. It is going to the quantum space. So quantum, what is quantum is? Quantum is whatever particle which is of size 10 power minus 9 to 10 power minus 15. Okay. Quantum is 10 power minus 9 to 10 power minus 15. If the particle size is between 10 power minus 9 and 10 power minus 15, then that particle is called quantum. Okay. What are those particles? Mainly electrons. So electrons, protons, photons. So these are some of the particles which is of size between 10 power minus 9 to 10 power minus 15. So if the particle size is between 10 power minus 9 and 10 power minus 15, that is called quantum. Okay. So with the particle, we are doing computation. Then that is called quantum computer. So nowadays we are doing computation with the transistors. Okay, emitter base collector. So the transistor size is getting very small day by day. So it won't follow the classical physics. It falls under the quantum physics. That means, so emitter base collector. So it will not stop. Even it will leak. Okay. So the actually we cannot reduce the size. So now the nanometer size is 3 nanometer. Our transistor size is 3 nanometer. Some mobile processors comes with 2 nanometer also. Beyond that, if you go, it will not follow the normal physics. So it will follow the quantum physics because the particle size is getting smaller and smaller. Okay. And in quantum computing, we are exploiting the quantum mechanics concept. Quantum mechanics principle is superposition, entanglement, and interference. Superposition means, okay, so there is a concept called quantum uncertainty, that is principle of uncertainty. That means at one point of time, if you measure the position of the particle, you cannot tell the momentum of that. If you measure the momentum, then you cannot measure the position. Okay. Okay. The quantum computer is not another computer which is so fast than the classical computer. It is completely different concept. Okay, it works on the quantum mechanics concept, quantum principle concepts. That is called superposition, entanglement, and interference. Superposition is at a particular point of time, particle can be in both the location. But if once you measure, it will collapse to one location. Okay. So entanglement. So once entanglement is created, that even the object is separated between two different location, the property remains same. Okay. So interference, another concept is there. Interference is, so if we went measurement, so yeah. So we are increasing the probability of correct answer and decreasing the probability of wrong answer by amplifying. Okay, we are amplifying the right answer, and that is a constructive interference. And with the destructive interference, we are decreasing the probability of wrong answer. We are increasing the probability of right answer by constructive interference. We are decreasing the probability of wrong answer by destructive interference. Okay, so computational basis. So classical bits, it can be either 0 or 1, but I think most of these things might be covered last 2 days, but I am just go through it. Okay, classical bit at any point of time, it can be in any one of the state. It can be in 0 or it can be in 1. But in qubit, it can be in either, it can be in both in 0 and 1 simultaneously. Okay. So this is a Dirac notation. Dirac is a Paul Dirac scientist. He proposed this notation to represent the qubits. Ket 0, Ket 1. This is called bracket notation. Okay. This is called bracket notation. Ket is a column vector. Ket is a column vector. Bra is a row vector. Bra is a row vector. Okay. Okay. What is superposition? So it can be simultaneously in. So for example, tossing a coin. You are tossing a coin. Okay. In the space, it is either tail nor head. Okay. It is in both the position. It can be tail also. It can be head also. Until you measure it, it is in both the state. Okay. So tail, for example, if you consider ket 0 as a tail and ket 1 as head. Okay. So alpha of ket 0 plus beta of ket 1, that is a psi. Psi is the wave function. Okay. So that means alpha and beta are the probability. Okay. So it can be 50% tail, 50% head. Alpha and beta are the complex number. So if you square it, alpha square plus beta square is equal to 1. That is total probability is always equal to 1. Okay. So just we are revising the matrix. Okay, reviewing the matrix multiplication. So this is how matrix multiplication happens. So A, B, C, D and XY. So AX plus BY plus CX plus DY. Okay, this is just for our understanding. Okay. So what is difference between matrix multiplication and tensor product? Anyone? Okay. So we can do 4 operations on one single bit. Okay. That is identity, negation, constant 0 and constant 1. And in quantum, everything should be reversible. Reversible means given the operation and output value, you can find the input value for A of x equal to B, given B and A using a unique find x. Okay. So if you give the output and the function, you can find the input. So operation which permute a reversible operation which erase and overwrite or not, identical negation or reversible, constant 0 and constant 1 are not reversible. For example, you have A plus B. Okay. What is constant function? So you have one function f of x, y, and if output is that. Okay. For any combination of input, for example, 0, 0, 0, 1, 1, 0, 1, 1. Irrespective of the any combination of the input, if your output is same, okay, then that is called constant. If the output is 0, then that is constant 0. If always the output is 1, then it is called constant 1. So constant function cannot be reversed. For example, output and the function is given. But for 0, 0 also it is generating 0. For 0, 1 also it is generating 0. For 1, 0 also it is generating 0. For 1, 1 also it is generating 0. That means you cannot find the input value. So it is not reversible. Okay. So you can perform 4 operations in one bit. Okay. That is identity, negation, constant 0, constant 1. Since constant 0 and constant 1 is not reversible, we are not considering it for quantum. So we are considering only identity and negation operation. Okay. 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 So tensor product. Okay. This is how tensor product is computed. Okay. You have one matrix. Tensor is this symbol. Okay. So throughout the slides, you will be encountering two symbols. Okay. One symbol is like this. It represents tensor. Another symbol is plus and round. Okay. This is XR. Okay. This is XR and this is tensor. Okay. So this is how tensor product is computed. So 1 into 3, 1 into 4, 2 into 3. So all the elements are multiplied each other. Okay. Then we will get this product. Okay. So in quantum, ket0 is represented as ket0 is represented as 1, 0. Okay. Ket1 is represented as 0, 1. So tensor product. Okay. Two two qubits. First qubit is 0. Second qubit also 0. Tensor product of 0, 0 is 0 is represented as 1, 0. Okay. Here 0 is represented as 1, 0. Okay. And then another 0, 1, 0. So we are doing tensor product of it. That is 1, 0, 0, 0. Okay. Easily you can do it. For example, if it is 0, 1, what will be 0, 1? 0 is represented as 1, 0. 1 is represented as 0, 1. And then the tensor product is like this. Okay. So usually in 2 qubits, we have 4 states 0, 0, 0, 1, 1, 0, 1, 1. 0 is represented as because 0, 0, first 0, 0, 0. This is 0, 0. Okay. And 0, 1 is the second. So 0, 1, 0, 0. And 1, 0 is third bit 0, 0, 1, 0. And 1, 1 is fourth bit 0, 0, 0, 1. Okay. Any doubt in this? Any doubt in this? Any doubt? Okay. So we will do tensor product of 3 qubits. Okay. For example, so 4 is represented as how 4 is represented? It is 1, 0, 0. 3 qubit. Okay. So first qubit is represented as 1 is represented as 0, 1. Tensor of 0 is represented as 1, 0. and then tensor of another 0, 1, 0. Okay. So instead of that, we know that 3 qubit means it has 8 state. 2 power 3 is equal to 8 state. Okay. So it will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. How to represent, since it is 8 states are there, so in the tensor product 8 value will be there. If it is 4, okay, this is 0, 0, 0, that means this is 4 is not, this is not 4, this is not 4, this is not 4, this is 3 only, 0, 1, 2, 3, this is 4, so 1, another 3, 0. This is the tensor product of 4. Okay, what will be the tensor product of 5? 5 is represented as 101. So tensor product of 5 will be, how we will write tensor product of 5? 0, 1, that is 1, tensor 1, 0, that is 0, tensor 0, 1, that is 1. So total product will be 0, 1, 2, 3, 4, 1, 6, 7. Okay. So another 2 zeros. So classical things, everything works on Boolean algebra. Okay, quantum things, everything works on linear algebra. Okay. So 5 is represented as 101. So it is 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. This is how 5 is represented with tensor product. Okay. We call this tensor representation of the product state. We can factor the product state back to the individual state. Representatively, the product state of n bit is a vector of size 2 power n. Okay. Okay. So there are a lot of logic gates, like in classical. Here also quantum also we have a lot of logic gates. Here we have single qubit gates, multiple qubit gates. Okay. So here 0 is represented as already we have shown, 0 is represented as 1, 0, 1 is represented as 0, 1. Okay, identity gate. So here all the gate is nothing but unitary matrix. Okay, so why it is unitary matrix? It should be reversible. Okay, given the input and the operation, you will get the output. Given the output and the operation, we should get the input back. So in that way, all the operations should be reversible. So all the gates should be reversible. Okay, so the gate is represented as unitary matrix. Identity matrix is 1, 0, 0, 1. This is not gate. Okay, X gate. This is represented as 0, 1, 1, 0. This is a Hadamard gate. This Hadamard gate actually used to represent superposition. Okay, used to create superposition. Okay, so 1 by root 2, 1, 1, 1, 1 minus 1. Okay, so this is how it is created. Identity gate does not affect any qubit state, and thus it is the same as the buffer in the classical circuit. So just it's taking the same state to the next level. That's all. It's a buffer. So ket 0. So that means identity of ket 0. Identity matrix is 1, 0, 0, 1. Ket 0 is represented as 1 and 0. Okay. So if you multiply, okay, you will get 1, 0. That is again 0. So it is, there is no change. Okay. Ket 0, output is also ket 0. So similarly, ket 1, identity of ket 1. Okay. Identity matrix 1 is represented 0, 1. So you will get again 1. So there is no change. This is identity matrix. So for NOT gate, that is X gate, unity matrix is 0, 1, 1, 0. Okay, x of 0. So x is 0, 1, 1, 0. 0 is represented as 0, 1. If you multiply, you will get 1. So if you apply x gate to the ket 0, you will get ket 1. Similarly, if you apply x gate, not gate actually, just negation gate. Okay. So we already discussed we can do 4 operations. Okay. First operation is identity. Second operation is negation. Third operation is constant 0. Fourth option is constant 1. Okay. So here, identity, negation, constant 0, constant 1. So we are not considering constant 0 and constant 1 in quantum because constant 0 is not reversible, because whatever input you give, the output will be 0. In constant 1, whatever input you give, output will be 1. So by getting the output and the function, you cannot recreate the input. So we are not considering these two things, constant 0 and constant 1. So we are left out with only two things, identity and negation. Identity we are doing and negation we are doing with X gate. Okay. And Hadamard gate. Hadamard gate unitary matrix is 1 by root 2, 1, 1, 1 minus 1, and the ket 0 is represented 1, 0. And so if you simplify it, you are getting this one. Okay. And Hadamard gate, if you apply to 1, ket 1, then it is becoming like this. Okay. So these 3 gates are single qubit gates. Okay. Identity gate, X gate, and Hadamard gate are single qubit gates. Now we will just brush up with the multi-qubit gates. If you have any doubt, please stop me in between. Is it audible, sir? Sir, madam, is it audible?
Yes, sir, it is audible.
Okay, okay. So please, any doubt, any interaction, we can just go with that. Okay. Any interaction? Yeah. Okay. So we will see.
Nothing, sir.
Yeah. Now we will see multiple qubit gates. C naught is actually 2 qubit gate. CC naught is 3 qubit gate, and C swap is also 3 qubit gate. Okay. So C naught, control not gate. Okay. Control not gate is, so if there is a, okay. So this is 1 qubit. This is another qubit. So qubit 0, Q0 and Q1. Okay. So this is the control not gate. If you're applying control not gate, this is the control bit. This is the target bit. Okay. Target bit. So if control is 1, then target will be flipped. If control is 0, target will be same. For example, if both the qubits are initialized to 0, 0 and 0. So now control is 0. Okay. And target is, so output will be 0, 0. For example, if another qubit, sorry. The control qubit, target qubit. Okay. If it is 1 and 0, so control is 1, so the 0 will be negated to 1, and this 1 will go as it is. Okay. Similarly, for 0, 1, 0 control bit. So no change. So here no change. Okay. So if you go for the truth table kind of thing, means it is 0 0 0 1 1 0 1 1. Output will be, if control is 0, so target is not flipped. So target is 0. If control is 0, target is not flipped. Okay. Target is 1. So if control is 1, target will be flipped. Actually, that is 1 1 actually. 0 0 0 0 0 1 1 0. So control is 1. So target will be flipped. So 1 0. Okay. So this is the matrix for C not gate. Control not. Okay. So here you can see. Here you can see this is the matrix, unitary matrix for C not gate. That means how here it is. Okay. Two quantum gate with one control and one target gate. If control bit is one, it applied not operation. Otherwise, it leaves the target bit unchanged. This gate is essential for creating entanglement and implementation quantum circuit. Okay. So here, if it is one zero 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 0 1 0 0 0 0 0 1 0 0 1 0. The control and target. Okay. So for first, this is a permutation matrix. Okay. This is not truth table. This is a permutation matrix. So here only for 0 0. Okay. 0 0, it is 0 0 only. For 0 1, 0 1 only. For 1 0, it is 1 1. For 1 1, it become 1 0. Okay. So here you see, this is actually 0 0. This position is 0 1. This position is 1 0. This position is 1 1. Similarly, here 0 0, 0 1, 1 0, 1 1. Okay. If 0 0, then output is 0 0. So here 1. If 0 1, output is 0 1. Okay. So in 0 1 position, 1 is given. If it is 1 0, it is 1 1. Okay. So in that 1 is given. Okay. If it is 1 0, it is, so if it is 1 1, it is 1 0. Okay. So this one position, this is a permutation matrix. Okay. Understood? Similarly, another gate is called Toffoli gate. Okay. Toffoli gate is 3 qubit gate. Toffoli gate is a 3 qubit gate. That is CC naught gate. Okay. CC naught. Control naught. So 2 qubits will be control. Okay. 2 qubits will be control and third qubit will be target. So here control, here control, and here negation. Okay. Here negation. So this is the Foley gate. So similarly here, okay, here how many things? So here you have so 3 qubit, okay, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 8 states. Similarly here also 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 1 0 1 1 1. Okay. For example, if both the, for example, here, if both are 1, then only the third qubit will negotiate. Okay. So 1 will come like this. So 0 will become 1. Okay, both the controls should be on, then only third qubit will be negated. Okay, for example, now if 2 qubit, this is the first 2 qubits are control qubit. Okay, this one is a target. Okay, similarly here also first 2 is control and the next one is target. So if 2 control, then nothing. So here it is 1 and other zeros. 1, 2, 3, 4, 5, 6, 7. Okay, so similarly here also. So why only for this, only for this and this operation, it will work. Otherwise, it is corresponding place will be so 0. Here it will be 1, 0, 0. So these positions will remain same. These positions will remain same. 0, 0, 1, 0, 0, 0, 0, 0. Here also 0, 0, 0, 1, 0, 0, 0, 0. Here also 0, 0, 0, 0, 0, 1, 1, 2, 3, 4, no, 1 here, 0, 0, 0. Similarly, here also 0, 0, 0, 0, 0, 1, 0, 0. Okay. Here, since both the first 2 control bits are 1, so this 0 will get flipped. Okay. So it will be 0, 0, 0, 0, 0, 0, 0, 1. Okay. Here also first two, so 1. So this will be flipped. That means output will be 1, 1, 0. Okay. So 0, 0, 0, 0, 0, 0, 1, 1, 0, 0. Okay. This is the matrix. So here you can see. So all other 1 are coming here. Here 1, 1, 0 become 1, 1, 1 and 1, 1, 1 become 1, 1, 0. Okay. Okay. So, okay, in classical gates, okay, so number of input and number of output is not same. Number inputs is more and output is less. So it cannot be reversed. Okay. And in quantum gates, it should be the same. Okay. Number of input and number of output should be same. Okay. So C0 gate is called Feynman gate, Richard Feynman. Okay. CC0 is called the Foley gate. C-swap gate is called the Federin gate. Okay. These are some of the information. I will share the slides with you. Okay. Okay. So reversibility and unitary in quantum computing. Quantum states are vectors in complex Hilbert space. That means it is a position of electron. Okay. Where it is. Okay. So quantum gates are represented by unitary matrix. Okay. So U dagger unitary with U dagger and this is equal to identity matrix. Okay. Any matrix the reverse, if you do, you'll get the identity matrix. ensure reversibility. So there is no information loss and preserve probability. Okay, these are the two important reason why we go for unitary matrix. Okay, so everything in the quantum is gates. Okay, but measurement is not a gate. Okay, so when the particle is in superposition, if you do measurement, it will come to any one of the state. Okay, when you are tossing a coin in the air, it is either head or tail, but once it come to the ground, it will fall to any one of the state, either head or tail. That is called measurement. Okay, measurement is not a unitary operator because after measurement, you cannot reverse to the original state. It is not, it is an irreversible operation. Okay, you cannot reverse it to superposition after measurement. So, and it is a probabilistic process. Okay, mathematical description is for 1 qubit in computational basis, M0, Ket0, Bra1. Oh, sorry, Ket0, Ket0, Bra0. Okay, this is Bra. Okay, so Ket1, Bra1. This projects a quantum state on the basis 0 or 1. After measurement, the quantum state collapses to the observable eigenstate. That is the energy level. Okay. Once you measure, the superposition collapse, the quantum state collapse. So psi function is a wave function. Okay, psi function is a wave function. Psi is a wave function. Alpha of Ket0 plus beta of Ket1. Okay. Alpha and beta are the probability amplitude. Okay. So modulus square of both the probability amplitude, it will give 1. Okay. So total probability should be 1. So modulo alpha square plus modulo beta square is equal to 1. Okay. So this is actually this M0, Ket0, Bra0, M1, Ket0, Bra1. This operation is called projection operation. Okay. Projection operation. This is a projection operation onto the state Ket0. 0 is a Ket column vector. Okay. 0 is represented as 1, 0 in column. If you represent Bra0, okay, it is the row vector. Okay. 1, 0, same you will mention in the row. So the operation Ket0 and Bra0 is the outer product. Okay. That is called inner product and outer product concept. If you do outer product, the matrix product is becomes 0. Okay. It is 1, 0 and 0, 1. Sorry, 0, 0. Okay. It is 0 only. Okay. Any doubt? Madam, is it clear?
Yes, sir. You may proceed, sir.
Yeah. So these are all the some of the concept which we want to know before going to the quantum algorithm. Okay. So concepts used is qubit superposition of state. Okay, Ket0. So alpha of Ket0 plus beta of Ket1 with the alpha modulo square plus beta modulo square is equal to 1. That is total probability is equal to 1. Okay, that is the probability amplitude. And second one here is multiple qubit combined with tensor product. So here tensor product is explained. Okay, how? Okay, so one qubit and another qubit means we are doing tensor product. Tensor product is multiplication and round. Okay, and plus round is XOR normal XOR operation. Okay, there are two operations actually it will come in this calculations. And this is the circuit. Okay, it carries alpha of Ket0 plus beta of Ket1 until you measure it is maybe 40% 0, 60% 1 or whatever it is. Once you measure only, you know, till now it is in superposition. Tensor product bilinearity. Okay, this is just so alpha 1 Ket0 beta 1 Ket0 tensor product of alpha 1 Ket0 plus beta 1 Ket1. So you can write it like this simplification. Okay, bilinearity. And then Hadamard gate. Hadamard gate, actually this is the gate, okay, which changes the basis from the computational basis to the X. Okay, there are three bases. Okay, in the Hilbert space or Bloch sphere, there are three axes: x-axis, y-axis, z-axis. So in the electron position can be measured in terms of any of the axes. In terms of x-axis also you can measure, y-axis, z-axis. Z-axis is the computational axis by default, okay? And x-axis is the Hadamard axis, okay? So to change from computational basis to Hadamard basis, so if you apply Hadamard gate on 0, it become 1 by root 2 ket 0 plus ket 1. If you apply Hadamard gate on ket 1, it becomes 1 by root 2 ket 0 minus ket 1, okay? So this is the unitary matrix of Hadamard gate. And measurement, okay, alpha 1 ket 0 plus beta 1 ket 1. So 0 and 1 is the probability, okay? Probability is mentioned as alpha square plus beta square, okay? Total probability is 1, so it can be in any probability. And once measurement, interference is happening, okay, interference will, there are two types of interference, constructive interference and destructive interference. Constructive interference increases the amplitude of the right answer. Destructive interference decreases the amplitude of the wrong answer. Okay. Okay, so today we will see Dodge problem, okay, Dodge algorithm and Dodge-Josa algorithm. Two algorithms we are going to see. Okay, so this is the first, this is not the practical algorithm. This is the first algorithm which demonstrate quantum supremacy or so quantum parallelism, okay? So quantum speed up, we can call it anyway, quantum speed up. So this function actually determines, okay, so this algorithm determines whether the function is constant or balanced. For example, irrespective of the input, if the function gives the same output, that is called constant. Okay, if the input changes, output changes means that is balanced. For example, you are having 4 inputs, 2 output is different and 2 output is another output, means that is balanced. For all output is same, okay, it is actually a Boolean function, okay, it is a Boolean function, complicated Boolean function with simple input and output. For every f of 0 and 1, okay, 0 and 1, okay, need to, for classically to check whether the function is constant or balanced, you need 2 evaluation, okay. We are now discussing about just one qubit, okay. So we need two instructions to find out whether the function is balanced or constant. For example, if you are giving 0 and output is 0, then okay, it is constant. Okay, if f of b of 0 is 0, f of b of 1 is 1, okay, then it is balanced. And 1 0, then it is balanced, but 1 1, then it is constant. For example, if you give 0 also output is 0, 1 also output is 0, means it is constant. Irrespective of the input, the output is same, that means it is constant. Okay, okay, so this box is called quantum oracle. This quantum oracle is, we don't know what is there inside, we don't know how it is implemented, but if you give input, it will give output. Okay, that is called oracle. No need to worry about the implementation of the oracle. Okay, so here we are creating the quantum circuit to find, okay, whether this function is constant or balanced. So we are initializing the first qubit as 0 and second qubit with 1 and applying Hadamard gate. Okay, this is psi 0. Psi 0 is a wave function. Okay, so in this timeline, it is like this. After applying Hadamard, what will be the mathematical equation? Okay, mathematically we can see. After applying this oracle, so we will get some equations. Then we are applying Hadamard in the first qubit. Then we are doing measurement. Okay, so measurement will tell you, okay, this function is balanced or constant. Any doubt? Okay.
Clear, sir.
Okay.
Sir, excuse me,
Ah.
can you please just explain that oracle problem?
Yeah,
Quantum
yeah.
oracle.
Yeah. So
Thank
oracle
you, sir.
problem is, see, we need to find out whether the function is constant or balanced. This is not a practical quantum algorithm. This is actually, this algorithm explains to the world that quantum is highly parallel. Okay, for example, you have a function, okay? You have a function, so you are giving 0, okay? 0 means output is 0. And 1 you are giving, then output is 0. Then you can call it, so for 0 also you are getting 0, and for 1 also you are getting 0. That means output is constant. But to know whether the function is constant or balanced, you should apply 2 times input. Okay, in one input you cannot say it is constant, or in one input you cannot say it is balanced. For example, first I am applying 0 to function. Okay, then I am getting output 0. Okay, second I am applying 1. That time also I am getting 0, means I can simply say it is constant. If I am getting 1 if I apply 1 to the function, if I get 1, then I can simply say first time my result is 0, second time my result is 1, so it is balanced function. Okay, so I need minimum two operation to determine whether the function is constant or balanced. But in quantum computer, in one single operation we can do. That is Dodge problem. Okay.
Thank you, sir.
Sir, one of the participants may ask the question. What are the qubits and superposition?
What are
How
the?
does quantum entanglement enable powerful computation?
1 minute. Chat.
Chat window was displayed, sir. Harshita,
Chat.
she asked the question.
Okay. So 1 minute, I'll just read out. Superposition. How does quantum entanglement enable powerful computation? Okay. So superposition actually it creates, for example, for example, if you have 2 bits, okay, you can do only 2 operations, but here 2 power 2 operations you can do. That means 4 operation. Okay, if it is 3 qubit, you can do 8 operations simultaneously. If it is 4 qubits, you can do 2 power 4, 16 operations simultaneously. If you can do, but in classical you can do only 4 operations. If you have 5 qubits, in classical you will do 5 operation, but in quantum with superposition you can do 2 power 5 operations. So okay, what are qubits and superposition? Okay, qubits is nothing but
Assign பண்ணுவீங்க 0 1 சிங்கிளா எடுத்துக்கிறீங்க.
yes. So qubits is a fundamental things. We can create qubits by several methods. We can create qubits by superconducting photonics based qubits, so anything. So but after that it is qubit. Okay, with qubit only, qubit is nothing but it is a electron's position or something. Okay, so it is in this position, means you are representing with some number. Okay, this qubit is just a position of an electron. Okay, then you are manipulating the electron's position. Okay, that is gate. Okay, so superposition is at single point of time, qubit can be in both location. So that is superposition. That means like our saints, they will be in 2 locations simultaneously. So they can do one operation in one location, another operation in another location. That is a superposition. So electrons can be in 2 positions simultaneously. But once you measure, it will come to one location. How does quantum entanglement enables powerful computation? Okay. So entanglement is actually there is a relationship. So you are creating bell pair. Okay. That means Hadamard gate followed by XOR gate. Okay. If you put in 2 qubit, two qubit entanglement, if you do, you have to do Hadamard gate. That means first you are creating superposition of that qubit, then you are putting XOR gate, then it become entangled. Once entangle actually mainly used for communication also. Communication it is used, and for computation also it is used. It can be in okay. So this state will affect the other qubits also. Building and maintaining quantum computers. So for building quantum computers, we need first of all qubits. Okay, that qubits you can get either from many techniques are there, either from photons. You can make photon as a see. Quantum is nothing but the particle which is of size 10 power 9 minus 9 to 10 power minus 15. What are the particles which are in 10 power minus 9 size to 10 power minus 15 size? Those are electrons, protons, photons. So these are the qubits actually. Electrons can be a qubit, photon can be a qubit, proton can be a qubit. So electron, okay, so electron, you are just giving some pulse. It is going to some location. That location is one value. And again, you are giving some other force to move that, okay, to that different location. Then that you are giving some force to move that electron, that force, that is called quantum gate. You are giving some force on the electron or proton or neutron or photon. Okay, these are the particles which are of size 10 power minus 9 to minus 15. These are quantum particles, and you are manipulating that quantum particle with quantum gates. Okay, then its position is changing. So if it is in this position, you are considering it as a, if it is in the north pole, you are considering it as a 0. If it is in the south pole, you are considering, or if it is in the north pole, anything, you are considering 0. And if it is in south pole, it can be in 1. So it can be, if it is in superposition, it can be both states simultaneously, but it is not limited to only 2 state. Qubit is only 2 state, but it can be in n positions. Electrons can be, if, for example, if you consider a sphere, ball, okay, earth, or if you consider orbit, in that orbit, electron can be in any position. Okay, so n number of position in that circumference, it can be in any position. So you can have any number of state. But for simplicity, we are considering only 2 state. That is called qubits. Okay. So you are creating qubits either by electron, proton, neutron, trapped ion. So how you take that electron, and these electrons are very, very sensitive to the environment. Okay, if there is a noise, temperature increase, so you have to maintain that qubit's position, because in normal temperature, automatically that electron will be very noisy. Okay, it will, you cannot find the position of that. Deterministically, you cannot tell. For example, if there is a ball, you can tell this is the position of the ball, but electron, this is the position, you cannot say. You can say, okay, probably it will be in this area. So that is a probabilistic. So you cannot say deterministically. So quantum, that's why quantum is not deterministic, it is probabilistic. So you cannot say electron will be here. For example, you cannot measure electron's position and momentum simultaneously. Okay, if you measure the position, momentum will be lost. If you measure the momentum, position will be lost. So at any one point of time, you can have only one value, either momentum or position only. Okay, if it is in the north pole, you can call it as a 1. If it is in south pole, you can call it as 0. If it is some degree angle, you can call it as some other state. So it can be in multiple state also. So if it is 2 state, then it is 2 power. If it is 3 state, it is 3 power. So that much state we can represent, but right now we are dealing with 2 states qubits. AI and cryptography, quantum computing. So cryptography actually now with the quantum computing, people are telling that this NP hard problems can be broken. Okay. So here our RSA algorithms works on the concept called prime factorization. For example, if I give 2 prime number, any calculator can do multiplication. If I give 2 prime number, for example, 3 and 5, okay, immediately any calculator can tell it is 15. But if I give 15 and find the 2 factors, it is little hard problem. Okay, for example, if I take 2 big prime numbers and if I multiply and if I give the sum to you, okay, find the 2 prime numbers, factor that prime number, means it is very, very difficult for even supercomputer. So, but this kind of problem can be easily solved by quantum computer, because quantum computer follows this superposition concept, so that highly parallel thing. So it will break the RSA algorithm. That's why people are going for different alternative. Okay, if quantum computer comes, real quantum computer comes in future, how to protect our security? So that this RSA things, this RSA mathematics, prime factorization things, they are just leaving, and they are going to different type of mathematics, kind lattice based or elliptic curve cryptography. So different concept they are doing. That is called post quantum cryptography. Now real quantum computer is there, but it is still not able to break the RSA algorithm. But in future it will break, so that now they are going for quantum safe cryptography. Okay, that is called post-quantum cryptography. Artificial intelligence, how it will affect artificial intelligence? So artificial intelligence need too much computing power. Okay, so right now we are doing with GPU. Okay, this ML, machine learning, training, everything we are doing with the help of GPU servers or HPC clusters. Okay, but this is not the right hardware for the artificial intelligence. Right hardware is quantum, so that a lot of model can be trained and huge data can be crunched. Okay. 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 So the Oracle encodes a function. Okay, the input state is prepared in superposition. So the function is evaluated on both the input simulation. Okay, so you just so here, for example, so here you see.
Hello. Sir, I have that one doubt, which is you have given Oracle, create the Oracle. So actually, what it means, how to encode in the first step.
Yeah, that we will see later. Now, at present, you don't want to confuse what is Oracle. So Oracle is some black box. Okay. So Oracle is black box. We don't know what is inside. But if you give some input, it will give some output. Okay. If you give some input, it will give some.
Okay, sir, got. So this is first step of the Dash algorithm. Sir, you're muted, sir.
Sir, you're muted.
Oh, okay.
Unmute yourself.
Yeah. So Oracle is a black box. You no need to consider what is inside Oracle. Oracle, just if you give input, it will give output. Based on the output, you can determine whether the function is constant or balanced in one step. Classically, it requires two steps. For single qubit, it requires two steps. For multiple qubit, it requires lot of steps. Okay, but for multiple qubits also, it will tell in one step whether it is balanced or constant. But there is no practical application of this algorithm. Okay, this is actually to prove that quantum is very fast than classical. Okay. Okay. So here we are applying 0 and 1 and then Hadamard gate. And then here for 1 also we are applying Hadamard gate. So here you see this Oracle takes input X and Y. Y is auxiliary bit. Okay. And X comes out as it is. Okay. And Y is converted into Y. This is XOR operation. Okay. This plus and round is XOR. Okay. Multiplication and round is tensor product. Y XOR of F of X. Okay. So here if you see, okay, in the first step, it is okay. In the first step, it is how it is transformed. So you are having ket 0. Okay. So for 2 qubits, we have to do tensor operation. Okay. So in the first psi 0 is psi is the wave function. Okay. So it will be converted into ket 0 tensor is multiplication and round. Okay. Tensor of ket 1. Okay. Then you are applying Hadamard gate. Hadamard gate is okay. Hadamard gate, if you apply on 0, it will become 1 by root 2 ket 0 plus ket 1. If you apply on 1, it is 1 by root 2 ket 0 minus ket 1. Okay. So once you apply Hadamard, it becomes plus state. Plus is actually x-axis. This is a computational basis. Normally it is in z-axis. Okay, in the Bloch sphere, it is in the z-axis. So now after applying Hadamard, it becomes x-axis. X-axis is called plus or minus. Okay. So now after applying Hadamard gate, so it become 1 by root 2 ket 0 plus ket 1 into, okay, into is tensor product 1 by root 2 ket 0 minus ket 1. Okay. So now you are just simplifying. So root 2, it become 2, 1 by 2, 0, 0, ket 0, 0, 0, 1, that is minus 0, 1, 1, 0, plus 1, 0, then minus 1, 1. You understood this step? So after applying Hadamard gate, the psi, okay, psi 1 will become like this. Okay, you understood? Shall we move to the next slide? So now we have to find out psi 2. Psi 2 is after applying this oracle. Okay, after applying this oracle, psi 2 will come. That means here 0, 0 means 0 is x. Okay, y is, this is x and y. Okay, this 0 is x, here 1 is y. Here x is 1, y is 0. Here x is 1, y is 1. So based on that, you have to apply 1 by 2, x become x only. So 0 remains 0. And here y is 0. So you have to substitute y as y is 0, 0 XOR of f of x. F of x is f of 0. Okay. So minus 0 is 0, x, because that is x. Then y is 1 here. So that means 1 XOR of f of x. X is 0, so f of 0. Plus 1, that is 1 remains 1, x. And then y is 0, 0 XOR of f of x is 1, f of 1. You understood? You will substitute like this. Okay. Next step will be like this. You are applying oracle to this. Okay. Are able to see? So, okay. So this is psi 1. Okay. Wave function is changing like this. So 1 by 2. So now we are applying this oracle function. Okay. Oracle is unitary function. That's is u of f. Okay, it's unitary function. Okay, u of f. Oracle is nothing but it's again a quantum gate. So two property it has to satisfy. One is unitary and reversible. Okay, so then it is called unitary function. Okay, oracle. So x and this is substitute. So u of f plus minus 1 by 2. So you understood, na? 0, 0. Okay, this is 0, 0. 0 is 0. X is x. Okay, this y is now 0. That means y XOR of f of x. F of x is 0. Okay, you understood? Now we are simplifying like this. Any doubt in this? Any doubt in this? Okay. Okay, we'll go to the next. Any doubt?
Sir.
Any doubt, madam? In the first step, it is ket 0 tensor of ket 1. In the second step, this is the equation. Okay. After applying Hadamard gate, it become like this. And in the third step, that is psi 2, it become like this. Okay. You understood, madam? We are substituting x comma y. So now y is y XOR of f of x. So y is now 0, 0. So that means y is 0, 0 XOR of f of x. f of 0 because x is 0. So minus x is 0 and y is 1. So 1 XOR of f of x. F of x is f of 0. So like this, we are substituting. Understood, madam? So next step. Okay. So now we are in this, this is psi 1 after Hadamard gate. And then after applying this, we are getting this. Then we are measurement. Okay. Then we are doing measurement. Hadamard gate again we are applying so that it becomes, again it is converted from plus state to computational basis. That is x-axis to z-axis. So here, finally it converts like this. Okay. So for example, if f is equal to f of x is equal to f of 1, that is called constant. If f of 0 is not equal to f of 1, then it is balanced. Okay. So here actually, if f is constant, measurement gives 0 here. If it is balanced, so based on this measurement, this qubit only, if you get 0, okay, then you can tell that this function is constant. If you get 1, here you can say it is balanced. So you are doing one operation here, one measurement. Based on this only you are telling, okay, whether this is constant function or balanced function. Understood, madam?
Sir, yes, sir, you can proceed, sir.
Yeah. So if constant, okay, that is f of 0 equal to f of 1. For example, if you apply 0 to function f and 1 to function f, the result is same. That means it is constant. So here in the previous equation, then you will substitute instead of f of 1, you can substitute f of 0. Here also f of 0. Okay. So that's how it is converting it. Okay. Then there is two cases. Okay. If function is constant, that is f of 0 is equal to f of 1. Another case is if it is balanced, that is f of 0 is not equal to f of 1. Okay. So based on that output, if the output is 0, you can say that function is constant. If the output is 1, you can say function is balanced. Okay, there are three bases: z basis 0 and 1 computational, x basis is plus and minus, Hadamard basis, y basis is like this. Okay, but here we are not using y basis. Okay. Okay, so quantum solution involves just one query. Okay, this is Deutsch algorithm. Okay, another algorithm is called Deutsch-Joshua algorithm. This is 1985, that is 1992. Deutsch and Joshua, both scientists, actually they applied this same concept for multi-qubits. So quantum solution Deutsch algorithm can solve this problem in one go. You might also, okay, so based on superposition and phase kickback. Phase kickback is, so here auxiliary bit is kicking back. Actually here the phase is changed. Okay, that means, see, this is electron position only. Qubit is nothing but electron. Okay, so you are doing some operation, that is you are giving some force, that is called quantum gate. So it can change the position or it can change this angle. Okay, so for example, if the electron is like, if you consider electron like a ball, okay, so electron is a qubit, okay, and you are applying some force to the electron, okay, this force is called quantum gate. So through some different gates, you are applying different force. Okay, so this force is called quantum gate. So once you are applying force, that is quantum gate, this electron can displace from one location to another location, or it can do spin, it can rotate. Okay, it can change its angle. Okay, it can change its phase. It can change to pi by 4 phase or pi by 2 or pi. Okay, so its phase can change. So here actually, if the function is constant, nothing is changing. If the function is balanced, its phase is changing. This qubit's phase is changing. If the phase is changing, you are determining that, okay, the function is balanced. If the phase is not changing, if nothing changing, whatever input is given, same output is coming, means so it is constant function. If the phase is changed, it is called balance function. Okay, how the phase is getting changed? So because of this operation, y XOR of f of x. So this is the auxiliary qubit. Here we are not doing, this is waste for us. Okay, but this operation, okay, this is the control, this is the target, but something happening in the target and it is inducing the control bit and it is changing its phase. Okay, that is called phase kickback. That is called phase kickback. Okay, the effect where the phase of the qubit is kicked back onto another qubit during a control quantum operation like C0 gate. So here, so phase of this 0, okay, x is changed based on the y. Okay, that is called phase kickback. So superposition and phase kickback. Okay. Okay, so here I explained what is phase kickback actually. So, okay, Dodge-Joshua algorithm. So here actually n qubits. Okay, in Dodge algorithm it is 1 qubit, but here it is n qubit, and here y will be only 1, not n. Okay, so Dodge algorithm provides a 2 times speed up in the computation. Dodge-Joshua algorithm provides an exponential speed up. Dodge-Joshua, okay, this is done by both 1992. Okay, so generating to n qubit, for n qubit problem, classical requires 2 power n minus 1 computation. For example, okay, if you want to find, okay, if the function has some n inputs, the function has n input. Okay, if the function has n input, okay, if the function has n input, two power n minus 9 plus 1 possibilities. For example, if so, here we have 2 qubits, so 2 power n minus 1 plus 1. So that is 2 power 2 minus 1, 1 qubit. Okay, for example, 1 qubit means 1 minus 1 is, okay, 1 qubit. So 2 power 1 minus 1 is 2 power 0. 2 power 0 plus 1, that is 1 plus 1. So it required 2 steps classically. If it is for 1, okay, if it takes 1 input, if the function takes 1 input, okay, if the function takes 1 input, okay, that is unitary of f. Okay, unitary of f. Then we need 2 steps in classical, but in quantum it does in 1 step. Okay, but similarly, if the input is more, if the input is more, for example, you are dealing with the 3 inputs, so then that is 2 power n minus 1 plus 1 query you have to do. Okay, to find out whether it is constant or balanced. So that is 2 power 3 minus 1, that is 2 power 8 minus 1, sorry, 2 power 2 plus 1. That means 5 steps you need. 5 times you have to ask, okay, whether it is constant or, so without 5 queries, you cannot find the function is constant or balanced. But in quantum, in 1 step, it can do. Okay, that is the quantum speed up. Okay. Classical required 2 power n minus 1 plus 1 computation, but 1 computation used in the Dutch algorithm. Okay. So prepare the n qubit in the quantum state 0. Okay. So you have to prepare all the qubits in 0 state, initialize into 0 state, and this ancillary bit you are initializing to 1. Then you are applying Hadamard for all here, and here also Hadamard you are applying. Then you are finding the equations. Then you are applying this oracle then you are applying Hadamard, then measurement. Okay. So here, if you get the same output, then it is constant function. If the output is flipped or if the phase is flipped, then it is called balanced function. Okay. So in one query, it can tell irrespective of the number of quantum gates. But in classical, you need this many steps. 2 power n minus 1 plus 1 steps we need. Okay. So there are two types of oracles. One is XR quantum oracle and another is phase quantum oracle. So quantum oracle allow user to implement solution without knowing the internal working of the problem solving function. So that is a black box. Quantum function in quantum algorithm is essential to solving specific problem and it is not limited to Dutch kernel. So anything we can, it's like a subroutine. In normal programming, we have subroutines. Okay, so in quantum, we have oracles. So you can implement oracle for any function. Okay, so not only for constant, and this is Dutch Josha is for finding out, but this has no practical things for anything. For example, Fourier transform or whatever it is, you can create an oracle for that. So inside you don't need to find, you just use it as a function. Okay, like a subroutine in the classical programming. Okay, I'll just run one program. Okay, so Oracle working process input. Okay, so this is the Oracle working process input to the function f. So you are giving one input, that is x. Y is actually auxiliary qubit, sometimes called the workspace or target, because in quantum number of input and number of output should be same. If it is 2 input, it should be 2 output. But in classical AND gate has 2 input but output is 1. OR gate has 2 input but output is 1. But so it is not reversible. So here everything should be reversible. Okay, unitary operator must be reversible. That's why the oracle is defined with XR. Okay, not overwritten. Okay, so you can XR type of oracle is there, phase oracle is there. So here XR oracle will be like this and phase oracle will be like this, f of x. That means actually for f of x, if it is 0, it is x. If it is 1, it is minus x. So only sign changing. So based on that, if it is same output is coming, means it is constant function. If the output is coming with a negative sign, then it is called balanced function. Okay. So for multi-qubit, how the oracle is implemented? Okay. Actually, this is completely mathematics. Quantum is nothing. You cannot understand quantum without mathematics. Okay. So same. So same I am explaining in different language. That's it. So two types of oracle, XR based oracle and phase oracle. Okay, there are other algorithms, Grover search algorithm. Okay, it gives it gives actually quadratic time speed up. Okay, it can be used in machine learning and AI. And Shor's algorithm, this is actually used to break the cryptography, RSA algorithm, that is prime factorization. And other algorithms, quantum Fourier transform. So these are actually building blocks for even RS, that Shor's algorithm also, this is a building block, quantum phase estimation, variable quantum algorithms. These variable quantum algorithms are used for hybrid. So nowadays, we do not have fully fault tolerant quantum computer. We do not have. Whatever quantum computer we have is noisy intermediate scale quantum, NISQ. So for that, we have to do hybrid. Okay, hybrid. We have to use classical computer also. We have to use quantum computer also. So that some part of the program will run in classical computer, some part of the program will run in the quantum computer. For that, variation quantum algorithms are used. These algorithms are used mainly in chemistry. Okay, chemical things. Variable quantum eigenvalue, finding eigenvalue, this all these things. And what are the challenges is hardware is limit. So now number of qubit is less. Even the qubits are very noisy. That means for one logical qubit, you need several hundreds physical qubits. So because it is noisy, so error rate is more. For classical computer, the error rate is 10 power 12. For a 10 power 12 operation, one error will be there. 10 power 12, 10 followed by 12, 0. So one error will be there. But for quantum, it is 10 power 3. For every 1000 operation, there is one error. So too much error is there. Decoherence. Before I complete the circuit execution, that superposition, everything is destroyed. Okay, that is that qubit is not stable. Decoherence happening, and okay, and more number of qubits are needed. Okay, even for cracking this prime factor numbers, we need more qubits. Current stage is noisy intermediate scale quantum, need hybrid quantum classical workflow. So now in future HPC, so through HPC they will integrate quantum processing unit. So now we are having a CPU, GPU. In future QPU will be integrated in the HPC. Okay, yeah, I will just show you one program. Just after that we will complete the session. Uh, Seven. So I'm just running Qiskit program. Qiskit is an IBM tool. Okay. Just running this Dutch Josh algorithm. Okay. So this is the Oracle implementation, and are you able to see the output? So now I'm getting the result 1. Okay. And this 1024 is, I'm running the circuit for 1024 times. Why? This is the number of shots. Okay. In quantum computer, okay, if you give 2 plus 2, okay, if you ask classical computer, what is the result of 2 plus 2? Always it will tell 4. How many times you ask, it will tell the same answer. But in quantum computer, if you ask 2 plus 2, sometime it will tell 4, sometime it will tell 3, sometime it will tell 2, sometime it will tell 0 also. So you have to run multiple times, and the maximum number of times it will tell the correct answer. So I'm running this same thing for 1024 times. So now I'm getting 1. That means this function is constant or balanced. Okay. See now, so f of x is equal to 0, so it's a constant function. Okay, I think it is. Okay. Actually, display problem. Okay, with X authentication. Okay, some issue in the graphics. I'll just open the program. So this is the Dodge Joshua implementation. Okay, so from Qiskit, import quantum circuit, transpiler. So what is transpiler? Anybody knows? So we know compiler. What is called transpiler? Anyone, please? Okay. So this is how the program will be. Okay. So we are defining the oracle constant. Okay, and balanced. And if you get 0, it is constant. If you get 1 or phase flip, then that is called balanced. But this quantum algorithm does not have any practical application, but just to prove that quantum algorithms are very fast. Okay. Yes. Okay. I'll show that. Yeah. Yeah. Yes. Yeah. See here. I can show. So this is the Dodge algorithm implementation. Okay. So first qubit is initialized to 0. So you are initializing second qubit to 1. That means you are putting X gate so that if you give 0, it become 1. So then you are applying Hadamard gate on this. Okay. Yeah. Second step, it is going step by step. So like psi of 0 wave function in this position, what will be that? This position, what will be that? This position. This is the oracle. Oracle is implemented with XR gate. Okay, this is the Oracle implementation, but we don't want to worry about Oracle implementation. This is just we can do with XR or phase change. Okay, this is how Oracle is implemented. This is Oracle. XR is the Oracle here now. For this, you can see the result here. F of x, not of x, balanced. So 1 means balanced, 0 means constant. Okay. So here, first time it is okay, constant, and balanced. Okay. Okay. So yeah. Any doubt? Yeah, that's all from my end.
Participants, please ask the questions. Any queries?
Sir, is it possible to practically prove these things, sir? Like when you have done the algorithm, is it practically possible?
This practically means it has no application, but this is practical only. So we are giving input.
Yes, sir, but you're using a simulation tool, sir. So I was just asking.
Practically
Whether you could
means
implement it on
okay.
some
Practically
hardware.
means you can have account in IBM quantum things. Now they are asking credit card information. Actually, I had an account, but now they are asking credit card information. Earlier they were giving. Actually, we can submit. Everybody will get 10 minutes actually. 10 minutes they are given free time, but now payment only. So a lot of quantum computers are there. So IBM has quantum computer. Amazon has quantum computer. Bracket, that their quantum computer is called Bracket, and Google has their quantum computer. They are giving some free time. And Amazon I don't know, but Qiskit was giving actually, IBM. We executed a lot of circuits in the real quantum computer also. They give 10 minutes time actually for month. But we do not have any real world application which can run in 10 minutes. Whatever our codes, it will run in seconds only. But now you can create an account in quantum.ibm.com. But they will not charge you now. That is free only. But they will ask you credit card details.
Oh.
Quantum.ibm.com. Quantum.ibm. Oh, 1 minute. I'll just share the link. Quantum.ibm.com. Actually, I had an account, but they are now asking for this credit card details. So here you have, okay, here you can do, composer is there, okay. You can just, so you can just create the quantum circuit. And here, for example, this is now 4 qubits and 4 classical bits. So we need classical bits because quantum cannot store anything. After measurement, it get collapsed, so you have to store it. For example, I'm just creating one circuit, okay. Just I am removing this. I need only 2 qubits. Okay, I'm just creating superposition with see here now both the qubits are in 0 state. Okay, so now I am applying Hadamard gate to this. See, now it become 50-50 probability. It is not in 0, it is not in 1 state. 0 0 is 50, 0 1 because I have 2 qubits, that's why 0 0. If I add one more qubit, okay, for example, if I add one more qubit, it will be 0 0 0. So 8 states will be there. 0 0 0 0 0 1, 8 states will be there. Okay. If I remove this, only one state will be there. If I remove this, 0 1, that's all. So I applied, I just removed this Hadamard also. Okay, so now it is in 0 state. When I apply Hadamard gate, it become half 0, half 1, 50% 1, 50% 0. So for example, you are creating something, okay, here, okay, some circuit, full adder, half adder, whatever it is. You are creating some circuit. For example, this is the X. Okay, so then here setup and run is there, okay. Here if you go, actually it will ask credential. So there actually it will have some 7 or 8 quantum computers are available. If you choose which quantum computer you want to run, then it will run and you will get the result. You can run the real world also. You should have an account actually. I have account. Let me try. I have account, but now it is asking credit card details. Now it is asking credit card details. Let's see. Other thing, they are not giving anything free. Other like Amazon bracket and other thing, they are not giving anything free. But still they are giving free. But only thing is they are asking credit card information. But you can do with you can do everything with Qiskit programming only. Let's see if you are lucky, then it should go. Okay, it is going. I can show running in the real program, real quantum computers if it allows. Just we are having some circuits. Just we are having all tie problems only. This is my account. So here, for example, quantum composer is there, learning function, workbook, computer resource, learning. So all courses, all materials, everything is available here. Quantum composer, okay, composer. So here actually, if you draw the circuit by just quantum gates will be there. If you just something went wrong, okay, they are not allowing actually. They are not allowing. First, I should complete that process. Credit card information I should give. Then only they will allow it. Learning. They are not allowing actually. Otherwise, it will come like this. And learning, if I give this one, it will run. Set up and run, and view job, it will run actually. It will display available quantum computers, and if you can choose any one of them, and it can run.
Is it speed is varying, sir? You said many computers are there.
Yeah.
Different.
Yeah, D wave quantum annihilers, yeah, you can do for quantum optimization. So they are giving a bracket, they are
Depends on the
giving time.
application, is it?
Huh?
Type of
Application.
quantum computer depends on the application.
No. This quantum annealer actually for optimization problem, that is not a proper quantum computer. Like that is not a general purpose computer. That only deals with only optimization problem, like traveler salesman problem, those problem. That is D Wave company, Canada based company. They are having that. They are selling also annealers, but quantum annealer is not quantum computer. That is only that specific purpose. But quantum computer, everything is now hosted in cloud, so you can get access through cloud.
Okay, thank you, sir.
Yeah.
So the participants may ask the question whether the transpiler convert high-level code to machine code.
No. Compiler will do that. Compiler, whatever Java, whatever program you are writing, it is translating high level to machine level. But transpiler is high level to high level only. High level to high level means we are writing Qiskit circuits, okay. But there are many quantum computers. That implementation is different, okay. So whatever we are writing, we can write the same style, okay. We can write in the same style for all computers, all quantum computers. But every quantum computer has different number of qubits, different kind of architecture. So it will convert our high level program to another high level program that which it can understand. That is called transpiling. Machine to
One
machine,
more
it will
question
different.
from participant side, sir.
Yeah.
Understanding what they are, how they differ from classical bits.
How they, because classical bit is nothing but switch. On means 1, off means 0. But here the concept is totally different. Based on the electron's position in the atom. So I initially told quantum means 10 power minus 9 to 10 power minus 15. So whatever the particle which are in between that size, 10 power minus 9 size to 10 power minus 15 size. Those are electrons, proton, neutron, photons, these things. So we are manipulating this electron and calling 1, 0 like that. If it is in North Pole, okay, that is 0. If it is in South Pole, it is 1. So like that we are calling. We are 10, that is called qubits. That qubit should be in the same state. It should not change. So that we are keeping, if it is superconducting qubit, we are keeping it in the absolute 0 Kelvin. So that we need dilution refrigerator. That's why that box, that all wires, everything, that is actually to keep that in that environment around 4 Kelvin, 3 Kelvin, or 0.2 Kelvin, like that. So we have to keep that electron in particular state. Otherwise, if it is the room temperature, now it will be in South Pole. Immediately, some wind will be there, or temperature will increase, dust will be there. It will go to South Pole, or it will go to some angle. So we should keep it in some position. Then we have to apply some force, external force. That is quantum gate. Okay, so you can apply Hadamard gate, XR gate, whatever Toffoli gate. That is external force, so that you can manipulate that position. And you are doing
Sir, you
computation.
mean to say, is there an intermediate state, sir, in between?
Anything, yeah, n number of states are there. It's not only 0, 1, 0.1, 0.2. You can make n number of steps. 0.11, 0.12, like that. And yeah, this is a continuous state. It's not a discrete state.
Okay, sir.
So they continuing the questions as whether the quantum computer tools and then basic components and the transformative applications of this technology in areas are drug discovery or material science or cryptography and optimization, which might be suitable to some of the applications relevant to the they are asking, sir.
Yeah, because right now what we are doing, we are using high performance computer for those applications. Okay, I think if I have QT03 or so research, okay. So research has 4 paradigms, okay. Observation, we have to observe first, and then based on observation, we have to create a hypothesis, then experiment. But every experiment, if you do, you have to spend a lot of time, you have to spend a lot of resource. Okay, so we are doing computation. Once the near result is coming, then we are trying that in the experiment so that the time to product is reduced. Okay, and we need actually a huge resource for, I don't know where it is. Okay. Okay, for example, if you see for weather prediction, okay, is it visible, madam?
Yes, sir.
Yeah, yeah. So for example, atmosphere is there, okay. Atmosphere model by dividing into 3-dimensional cells, calculating of each cell repeated many times to model passage of time. Suppose whole atmosphere, okay, we have 5 into 10 power 8 square miles divided into cells of size 1 mile into 1 mile into 1 mile to a height of 10 miles, 10 cell height, that become 50 into 10 power 8 cells, okay. So that much cells are there. Suppose the whole atmosphere 50 into 10 power 8 square mile divided into cells 50 into 10 power 8 cells. Suppose each calculation requires 2000 floating point operations per second. So here we are not doing anything integer, madam. For scientific application, we have to do floating point operation. We cannot omit anything. For example, if it is 5.6.0001, that value also we cannot omit. So floating point calculation only we have to do, float, integer, double, like that. So in one step, 10 power 13 floating point operations per second necessary. Okay. To forecast the weather for over 7 days using 1 minute interval, it takes this much. So 10 power 17 flops. The computer operating, my computer has 0.384 teraflop. So for 50 minutes interval, if you want weather prediction, 34 teraflop is needed. So like molecular dynamic simulation. So nowadays we are doing for smaller molecules only, hydrogen with less atomic number. If you want to do the complete reaction, then that much resource we do not have in HPC. That's why we need quantum computer. And drug discovery, for example, that molecule, whether that drug binding, whether it will bind. Sir, there are multiple combinations you have to check. So that means a huge computation is required. That much computation we do not have at present. So only quantum computer can do that because it is completely parallel. Because for example, if I do 10 power 8 operation, I need one computer. Okay. For example, if I have, if I increase my size, my problem is exponential, madam. But my resource is not scaling exponentially. For example, I'm calculating for 10 atoms. That means 2 power 10 operation or something. Let's consider. Okay. So I need 100 servers, HPC. If I do for 2 power 11, then I need 200 servers. 2 power 12, I need 400 servers. 2 power 13, I need 800 servers. So my problem is scaling linearly, but my resource requirement is scaling exponential. So, but here qubits, one more qubit if you add, it will match. Here one more qubit because that is 2 power. Understood? No? Any other doubt?
Sir, one more person is asking the question.
Yeah, yeah.
Emerald value of 0, Cx of 0, 1, x of 1. What is the circuit output or what is the mathematical output
Which one, madam?
while executing? It was
Can you
displayed in the chat window, sir. H
That
of
will
0,
be
C
okay,
x of
okay.
0, comma 1 and x of 1.
Okay, 1 minute. H of 0 is Hadamard. You are applying
Hadamard.
Hadamard gate to the first qubit. Okay.
Yes, sir.
Okay, okay. For example, we will draw that. Okay.
இப்போ இதுல வந்து ரெண்டு
So how many qubits, madam? This is, for example, this is 1 qubit. Okay. So here you are applying Hadamard on qubit 0, H. So it become 1 by root 2 ket 0 plus ket 1 mathematically. Okay. C x of 0, 1. That means this is 0th qubit and this is 1 qubit. So here you are applying C naught gate. Okay. So then x of 1. What is x of 1? So you are applying, okay, x gate in, okay, first qubit. Okay. Okay, understood. So here you are applying x gate in the first qubit. Okay, madam. So what is the output? Okay. Okay, I will rewrite again. So qubit 0, q0, q0, q1. Okay. By default, it is initialized to 0 only. Initial value is 0 only. So here this is the, okay, h, and here it is the C naught. Here qubit 1, you are applying x gate. So for example, okay, here now both values are 0 only. Okay, after applying Hadamard gate, now it becomes superposition state. That is 1 by root 2 ket 0. Now this is 1 by root 2 ket 0 ket 1. Then, so since here you are getting now this is entanglement is created. Hadamard followed by C naught, entanglement is created. Okay, this is pure entanglement. That is 1 0 0 and 1 1 state is created. Okay. Then you are applying X gate to this negation. Okay. So 0. So here we have to do mathematically then. By root 2 get 0 plus get 1. We can better do it actually. In program, we can do it easily. Here QC, we are creating 2 qubits and 2. First is Hadamard gate on Q0, 0 to 1, and X gate you are doing. Okay. X of 1. Okay. It is 2. Actually, I am running 500 times, madam. 246 times I am getting 10. 254 times I am getting 01. So more probability is 254. So it is 01. I can increase the number of shots also. I'm just if more shots actually give more probability. Probability will increase. If it is if I run for 100 shots, if the probability is 70%, if I increase the number of shots, the probability will increase. Let's see now. 1000 shots I'm running. 10. That visualization we have to do. Yeah, visualization we should develop actually. Anything else?
Thank you so much, sir. Thanks for your patience. They are asking so many questions. We are patiently answering for that with an execution mode. Radhanaran, sir, please propose the thanks message.
Really, it's a wonderful section, sir. We are enjoyed for past 2 hours, but we don't feel bored. You are taken a full section with a full knowledge.
Thank you, sir.
We
Actually,
have
everybody is
to
learning.
bear
This
with
is a
you.
very new
We are
field.
having so
So
many doubts on algorithms. So maybe we will have after one more section later, and we have to learn more from you, sir. So I sincerely thank you for delivering your excellent lecture regarding the representation of multiple qubits, operation on qubits, and tensor products, and we are discussed about different types of algorithms. So really, it is a very knowledgeable section, and you are explained in a clear manner and deep insight in advanced concepts. So we truly appreciate the time of effort you given to us and making a section as a valuable sections. So we looking forward to your interaction and guidance in future. Thank you so much, sir.
thank you, sir. Thank you. Yeah.
Sir, most of the participants are asked the presentation, sir. If possible, kindly share your PPT
Yeah, I
through
will
our
share
mail,
it.
sir.
I will share it. Yeah, I will share it.
Thank you, sir.
Yeah,
Now I
thank you.
invite Mr. Rajshekhar to invite the resource person too. Rajshekhar, sir, please.
Yeah. So I can discontinue, madam.
Yes, sir. Thank you so much.
Thank you. Thank you. Yeah, thank you.
Thank you, sir.
Thank you, ma'am.
Thank you.
I'm very happy to introduce our alumni and also in this session resource person, Mr. Ravi Shankar. Mr. Ravi Shankar is a seasoned IT professional with over 15 years of extensive experience in the technology industry. He is currently working as a tech lead at Infosys, Texas, United States. He has been consistently delivering value through his expertise in Java development, cloud technology, and enterprise level solutions. Based in Fort Worth, Texas, Ravi Shankar plays a key role in leading teams, architecting scalable applications, and driving digital transformation initiatives for global clients. He began his academic journey with Bachelor of Engineering in Computer Science from Vinayaga Mission Kripananda Warrior Engineering College, Vinayaga Mission University, Salem, which leads a strong foundation for his career in software engineering and emerging technologies. Over the years, he has honed his skill in solution design, application modernization, and cloud adaptation strategies, making him a trusted professional in his field. Beyond his technical expertise, Ravi Shankar is also for his strong leadership, mentoring ability, and commitment to delivering innovative solutions that align with business goals. His career reflects not only technical excellence but also a passion for continuous learning and adapting to the evolving IT landscapes. Welcomes you once again, Mr. Ravi Shankar. This session will be hand over to our resource person.
Yeah, thank you so much, Rajsekhar. So Rajsekhar is my so we both in the same branch and same class also in the college time. So really I'm appreciate to these kind of brief introductions about me. Thank you, Rajsekhar, and thanks for this opportunity to win a mission. Yeah. Okay, so maybe, yeah, let me share my screen. So am I audible, everyone?
Yes, sir.
Thank you. Yeah, let me share my screen. Okay, so I'm sharing my screen. So the PPT, this topic is about to explain the quantum algorithm, how it's solving the problem. So I will give you some. I hope there are more sessions you already had. You might have some understanding about the quantum algorithms, quantum computing. So let's explore more about some real world use cases. So I will give you some examples. So what algorithms we are going to see, and what is the example, what kind of problem that algorithm going to solve in the real world. Okay, so let's start. So this PPT is prepared from the beginning. It start with the quantum basics, so that I can it will be refresh your quantum basic understanding, and then so how it is solving the problem and all we can see. So let's explore how quantum mechanics help us to solve impossible problems. So if you search the quantum computing in the Google or anywhere, so the first thing you will see, there is a quote, the famous quote from Richard Feynman is, if you think you will understand the quantum mechanics, so you don't understand the quantum mechanics. So it's really, there are more things to learn about the quantum mechanics. So don't think we understood the quantum mechanics. So still there are a lot of things to understand. So we have to think a lot. This is the code you can see everywhere if you see search in the Google about the quantums. Okay, so why quantums? Okay, so I hope there are classic computers. It cannot solve the complex problem. So if it is a complex problem, so classic computer is reach its limit. Okay, so then the quantum is coming into the picture. So it is the quantum mechanic is entirely a different rule, a new rule it's creating to solve the problems. Okay, so that's why quantum we are keep looking. So just think, yeah. So just think of versus classical versus and quantum. Okay, so just think there is maze. So the maze is if you're entering a maze, so you need to come out from the maze. So there is a lot of way to go, and in some way you will stop, and again you have to start the another way to go out of from the maze. Okay, so the classic computers and it is try the possibility one after the other. So then finally it's find the right path. It is the every possibility path it is executing in a sequential manner. But the quantum approach is entirely different. It's simultaneously it is go the path for all the possibility waves, and then it reach in a right time. So all the possibility waves it start at the same time, and we reach we reach the output at the instantly and fastly also we reached output. So that is the quantum approach. So that is the difference of classical and quantum. It's one after the another. So one by one it will execute, but the quantum is it has simultaneously execute. So then what is the quantum algorithm? So these are the recipes for the quantum algorithm: qubits and superposition and entanglement. So we already explored some information. Anyhow, again I'm explaining about this, so it is fresh for you only. So the qubits are capable to store 0, 1 and both values at a time. Okay. The superposition is it is allow qubits to exit in a multiple state at once, and versatility increase the component shell capacity. So the entanglement, it's become a it's connecting all the qubits interconnected, so that the state of instance influences the other enable complex parallel computations. So it is interconnected, so that it can be processed the it can be processed at a parallel time. Okay. So these are the three recipes being used in the all the algorithms. Okay, so the power of parallel cells. Okay, so there is a classical approach and quantum approach. Just imagine in a store there are more boxes, so you want to find a specific item from the box. So let's example take some so one pen I have to take from the box. So you need to find that pen is in which box it contains. So you have to open the box one by one and see whether pen is there or not, right? So the classical approach is it will open one by one. The person, if one person is let's see the one person is playing that in the classical computers and then quantum computers. So the person is opening one by one and finding the pen finally. So it takes some times. Okay, but in quantum approach, so just imagine, so by yourself opening all the boxes at the same time. So like a picture. So in a picture, right? So at the same time you're opening one box, all the boxes, and immediately you can take a pen at one. So it's little it's very fast. So that's why I'm trying to explore about the parallel. So parallelly you are opening all the boxes and finding a pen. Okay, so the problem, so what kind of problem the quantumist tackles? To search to find a specific item, and then for the cryptography, so creating a new high secure encryption methods. So the optimization to solve the complex logistics and scheduling then resource allocations puzzles. So the simulations, accuracy of modeling molecules and material and physical system. Because these are the quantum is tackling these areas actually. Okay. So the algorithm is Grover algorithm. This is a super charged search engine. Okay, so significantly speed up the search for specific item within the unsorted databases. The efficiency is to find a needle in a haystack exponentially faster than the classical methods. So let's see some another example. For example, so you lost a ring. You lost a ring in the beach sand, and in beach there are more crowded. So you want to find the ring in the beach. So beach is very big, and there is crowded also. How will you find? So in this kind of problem, the quantum solving. So for the search, the Grover algorithm is really helpful to search this kind of complex problem also. So the database searching is the application and optimization problem, and even breaking some cryptography has functions. Okay, another algorithm is SOS algorithm. It's a encryptions challenges. The SOR algorithm can efficiently find a prime factor of very large numbers, so which had problem for classical computers. It's very hard problem for the classical computers to find the prime numbers, to use the prime numbers to do the encryptions. The impact is so threaten the security of current public encryptions standards like RSA, so which rely on difficulty to factoring the large numbers. So the encryption is everywhere it is using. So if you do a transaction, so bank transactions, if you do send the email with secure, so in wherever it is secure, the encryption is using everywhere. Okay, so for that encryption, the mostly it's use the RSA. But if you want to use the prime number to encrypt the particular thing, so it's very hard for the classical computers. So that the quantum is can handle with the prime numbers to do the encryptions. Okay, so the future is to drive the development of post-quantum cryptography. Okay, so the quantum simulations. So the quantum simulations unlocking the new discovery. So the quantum computers can simulate the behavior of atoms and molecules at their fundamental quantum levels. The precision is the model complex chemical reactions and the material properties with the unprecedented accuracy. The breakthrough here is accelerate the drug discovery and material science and clean energy research. Yeah, so it's really accelerate for the drug discovery. So for everybody knows, right? So for if one drug, if they want to release, so there are more years of trials, more samples of trials the company has to do. So then only it's come out for the usage. So in those areas, the quantum is really using to speed up for the release. It can be a faster evaluations for the drug, and it's released quickly. So just think, there are more unsorted disease still we have in our society. For example, so there are more cancers very is there, right? So it helps to improve to find a drug discovery for in these areas. It's really helpful for the quantum. So we are looking for that in future for us. And the quantum leaps, exploring the future of computing. So by this stage, it's clearly, and the quantum computing is more than theory. It's transformative force, redefining how we solve the problem as the field advance. So in these areas, the quantum is entering in the future. So optimization, logistics, and supply chains. So is the domain. It's really so I'm working in logistics domain. So I can give you some more example in the logistics. in the logistics mostly, so we have to containers here and there all over the world. One night, if you want one item, so that can be possible in the everywhere in the online systems. If you want to purchase in the Amazon, so it is coming from the US and it's coming from the other places. So in these kind of situations, mostly the company required is how to deliver a particular items to the customer for the customer satisfaction, and route optimizations. So in which route is the easiest way, and so if we reach that particular locations, what is our business growth will be there if we deliver there. And then in so cost effective. So the mostly the logistics companies are thinking about the cost effective. So how fast we can deliver and how much cost we can reduced to deliver the product. Okay, so there are more logistics companies are investing in the quantums to solve these kind of problems. Okay, and in healthcare, the drug discovery, as I explained before, and molecular simulations, and AI and machine learning. It's now we are in the AI wave. So already we are doing some research in the AI. We are some people started using AI in the AI is available for the for everyone in the mobile also, right? So even more faster, how can we do faster and smarter models? So coming the picture, and cybersecurity. So new defenses and challenges, and in global innovation space, the government and tech giants are doing. And so as a quantum journey, so what we will explore today is the quantum realm and the optimization power, and quantum and AI synergies. So real world impact and challenges on progress, and what is the demystifying myths. So we are going to see about these topics also today. Okay, so just understanding the quantum realm. So I'm as I explained before, and you're already aware about this. The bits. So classic computers are using bits, so zeros and one, 0 or 1. But the qubit is it's not just a 0 or 1. It can be both simultaneously. Okay, and then superposition is allow qubit to represent the multiple state at once. So it's increasing the computational power. So just imagine the coin. So the coin is head and tail, you can see. So if you flip the coin, it's spinning in the air. So during the spinning, at the time you can see you can visible the both sides when it is spinning, right? So that is called the superposition. Okay, so that can be really the qubits. It is kind of way to check actually. Okay, so the zeros and one, and quantum computer is having 0 or 1 and both at once. And another algorithm is QA and OA. So quantum approximate on optimational algorithm is a prime example of how the quantum computing tackles the real world challenges. Okay, so there are versatile applications. So in the logistics area, as I explained, right? So optimization delivery routes and reduce the fuel consumptions, and then delivery time. So these are the main things for the logistic thing. So we have to deliver at the right time and faster also. And what is the cost effective for delivering the product to the customer? Okay, in the financial, the finance, so portfolio optimization and risk analysis for the complex market model. So energy grids, so managing energy distribution to improve efficiency and prevent blackouts. In the telecommunication area, optimizing the network traffic and bandwidth allocations. So in the healthcare, the scheduling hospital resources and designing optimal treatment pathways. So in AI and machine learning, enhance feature selections, clustering, and neural network training, and streamlining the productions works and supply chain optimization in the manufacturing companies. So in these areas, the QA and OA algorithm is being utilized. Okay. And quantum and AI. So the synergies between quantum computing and artificial intelligence is leading to ground breakthrough advance, particularly for the QML, quantum machine learning. So enhanced pattern recognition. QML algorithms can process and find intricate patterns in the word databases, and they are invisible to the classical algorithms. So to boosting the classical machine learnings, the quantum processors can act as a powerful accelerator or traditional machine learning task. So making existing AI models even smarter and faster. So the new horizon here is the combination of quantum and AI. It's opened doors to solve problems. So currently it's intractable, it's unsolvable. Those kind of problems are open to solve if quantum and AI is combined together. So the material advancement is material discovery to move more accurate and climate modeling. Okay, the real world use cases here, where the quantum quantum science. So drug discovery, so simulating the molecular interaction to the accelerator the development of new medicines and the new therapies. It's also helping for going to help for the new therapies. And in the battery design, so designing more efficient and long lasting batteries for electric vehicles and renewable energy storage. And in the supply chain area, so optimizing the complex global supply chain, the logistics from manufacturing to the delivery, and maximum efficiency. So these are the real world use cases. So the quantum advantages, it's a kind of a race against the complexity. Okay, the key insight here is it's not about being faster at everything. Okay, it's about to solve this specific and exceedingly the complex problem. So those are all not resolvable by our supercomputers. Okay, so the matters of quantum is optimization, solving problem in logistics, finance, and manufacturing. Okay, and the science and healthcare, so modeling moleculars for drug discovery and material designs. So the cryptography, so breaking existing encryptions and driving in the need for the new quantum safe and security. And in AI and data, accelerating the machine learning and big data analysis. The milestone examples, so the Google and 2019, the Sakimura processor is with the 53 qubits. It's completed a task in 200 seconds that would take the supercomputers 10 years. So it's much faster. So in recent this year, so Google also done another trial, the Willow processor with 105 qubits. It's a stable with 5 times longer than the previous trial. There are some milestones we are achieving every year. So the Google is achieving this. Okay. The navigating today, the quantum challenges is so qubits, the Frankel qubits. Qubits are incredibly delicate and easily disturbed by our environment noises and leading some errors. And in the extreme conditions, the many quantum computers require operations at temperatures nearly about absolute zero to maintain the qubit stability and the error corrections. So developing a robust error corrections and mechanisms is crucial to ensure reliable quantum computing. These are the current challenges we are facing. So keep looking forward to the fault tolerance. The quantum computing myth versus reality. So everybody have a questions like quantum computers will replace our laptops and smartphones. So you won't browsing a social media or checking emails in the quantum computers anytime soon. It's something specifically and specialized machine, not like our regular computers. It's to really looking for to solve the specialized and complex problems. The quantum computers are extremely complex and specific problems. So the excellent task is like drug discovery and financial modeling and AI optimizations that are impossible for classical machines. Okay, so the quantum computing beyond the hype, not just a hype. The quantum computing is moving from theory to real world. It started moving from theory to real world. It started exploring more about the quantum, and some trialists and some experimentalists already started, and we are keep trying it. The unique power of the quantum is use superpositions and entanglement to process the information in a way classical computers cannot. The focused impact here is the quantum machines won't replace the classical computers, but will complement them for specialized and complex problems. So our tech giants and startups and governments are started investing billions and billions to the quantum computings to build our scalable quantum systems. It's actively progress. Still, there are some challenges on the error corrections and stability of the qubit and scalability of this qubit. The breakthrough here is accelerating. So the roads are ahead. Okay, so let's start the quantum journey. So ready to deep dive in the quantum and start exploring and start experimenting. So there are some so open source tools is also available. And in the previous session, the Anand has explained about the Qiskit, and in Google also have CARQ, the platform. We can explore more and join the community, join the forum, online forums and local meetups and quantum hackathons, collaborate with a few and experts with to innovating the quantum applications. And if you join, we will get some more knowledge about this. Okay, we'll start the journey. The key takeaway here is the quantum is a new way to solve the problems. The quantum computers tackle problems intractable for classical machines, open doors for the previously impossible computations. And the algorithm, the maze, there are encryptions, breaking algorithm, SOR algorithms, and then to solve the optimization complex problem, so Q and OA algorithm, and to searching the searching mechanisms, it's using the Grover algorithm. So these are the algorithm is being used. And the industrial transformation is like expert the revolutionary change in the medicines and finance and material science, AI and logistics and the quantum capabilities. So these are the takeaways we have to think from this meeting. Yeah, so that's all my presentation. That's all my presentation also. So if you have any questions, please post in the chat also. And our group members are actively checking the questions.
Hello,
Participants,
sir.
please post
I
your
have
questions
one
in the chat window.
question. Sir, can
Hello.
okay.
Yeah.
Ma'am, you may ask the question now. Sir, what is qubit? How does it differ from classical bit?
Yeah. So the qubit, so the classical computer is having bits zero. It can be a 0 or 1. In the previous session also, the Anand explained like it's a switch. Either you can off or on. So that is one example. So the qubits can have zeros and one, or both values also can be present. So that's how we have differentiate the qubits from the classical bits.
Can you give some basic material for quantum computing to refer beginners? That is, they are asking any textbooks for beginners of quantum computing. Can you suggest, sir?
So even when I am searching in the Google, I will also, there are more short videos is available, but even I'm also looking for the proper channel. But in Anand also, in the previous session, he suggested like we can start using the QZ kit and register the kit, and there some have some learnings materials available. I hope I can also suggest the same way. So registered in the QZ some of the tool, and there we have some learning the way of channels. So that is the best
Even
way
in
I would suggest.
IBM tool also Q Cycled, it is an open software tool. It might be useful to getting a better implementation results. In the previous session, he was handled. That free trial demo sessions are also available on that IBM toolkit in quantum computing itself. Sir, one more question. how does the superposition will differ from qubits?
So superposition is like so the qubit is can have 0 or 1 or both values, but the
Science in healthcare and
superposition is
supply
like
chain.
it's a like of I have given an example like coin. The coin, if you flip the coin is spinning in the air. So even we visible. So there are more while spinning we can see both sides in a same time. In a one way we can see both what is tail and head it will be spin. So that is a superposition. So that's how the example I can search and give you that. So I don't have any other example for these superpositions.
So how so for the quantum signing, which will be helpful to that healthcare and supply chain technology?
Yeah, yes, it's helpful for healthcare. So there are so new drug discoveries. It's really helpful. So if, I have given some example also in a real world now. So if even one drug, if it is released to the customer to use, it has a many years of trials and many samples. So that was more than a 10 year, 15 years. So if quantum comes, so those years can be reduced. The drug can be released faster to use in the healthcare. So we can think on that way. In the supply chain also, supply chain is like to delivery. So the example, the Amazon in Amazon we can order any country of product that can reach to our the customer. So but the company is thinking about how faster and how can we deliver with cost effective. So with the custom, finally the problem, the business here is the to solve the customers problems and faster manner and then efficiently. So in the supply chain also, the quantum is helping in that way.
Java applications.
Sir, whether it might be implemented only in the Python language or it may support to using a Java platform. The implementation of this quantum qubits.
Yeah, actually, I'm also in the learning stage, so I have not explored much in the program level. Maybe I can explore and answer the later of these questions.
Dear participants, any more questions?
Sir, actually, we have seen that you are working on a Java platform. So, can you share your idea how maybe it is related, quantum is related with Java and how you are doing?
Yeah, so we have not started exploring with quantum actually in from the language. So it is in a trial manner only, right? So still the research is still going on. So I am part of working in the in the industry like logistic industries to for the particular applications. So we have not started using it for our real world now. So still it's a knowledge we are gaining, and still the trial is keep on. The trial is going on from the Google or IBM. So maybe it takes some more years to involve in the program or applications in the real world programs and real world applications. So right now, even I don't have idea about how it is be, but I as I explained, like in these areas. So wherever the large scale of business and still there are some applications like still our Java application is we are using for some multiple business multiple applications like so in a daytime, what are the activities being done in the our logistic industries, like loading the container, unloading the container, and then the container is travel to another place. So in all over the world, so we are keep monitoring in for the not only for the one item. So we the application is handled for the large scale of containers. So in these areas, it is currently working on with the Java applications. So as a quantum point of view, so the whatever process currently we are doing, for example, for one application, if we run the batch applications can run for more than 1 hour to process entire world of containers. Okay, so it takes 1 hour. Maybe the quantum can come in the picture and to reduce the time and to reduce some of the resource to solve the problem, the so that the client can beneficially to reduce the resources, and then to it might be a cost effective for the clients. So maybe I can think on that way. It could possible.
So participants, any
I
questions?
think
What is the principles of superposition space?
yeah. Again, I will give you the same example. I don't have another example for the superposition. So the same thing. So when you spinning the coin, we have some lot of the spinning items. If you spin, you can see both the sides at a time. So that is the only the principle. We can see what it's present and what is the value present in the qubits.
So one more question. Can you tell me the limits of superposition states? The states of superposition.
I think so. Still, I need to think about this answer for this question. Even I'm also tell you right. I'm also learning stage. So maybe we can take out this question and we can research and the answer for this.
Sir, actually, how the artificial intelligence integrates with quantum? Any idea, sir?
Integration with quantum. So, for example, so just a thought. So now we have the AI tools are available. We started using ChatGPT, and then there are some Copilot is started using in all other companies. So now the AI, whatever result we are searching, we are giving the input. So we used to call prompt. Whatever prompt we are giving for the AI, it's giving some result. So it is not a right result. So if you search, it will give you some output. So based on the data, what the system has, so it's providing the information. So it might be a correct and it may not be a correct. But when quantum comes in the picture, it can be the possibility of correction is the possibility is more if quantum coming in the AI. So maybe if you prompt the prompt to the AI, so it can give the output at the maybe 70 to 80 or 90 percentage or 99 percentage can be correct answer. So when the quantum and AI it's together, and even more faster also. So nowadays we have started using, so we can relate the output of 60 to 70 percentage or 50 to 60 percentage can be a correct. So we should not trust always the AI. So it's just for our knowledge we can learn. So when the quantum coming the picture, we can think the possibility of correct answer is more than 80 or 90 like that.
One more question, sir. Actually, came across your slides. I saw that the race against the complexity of quantum. Actually, I can't able to understand that slide. Can you please go across once again, sir?
1 second. Race across. Yeah. Yes. So do you want to share? Do you want to share my screen?
No problem, sir. You can just.
Yeah, the race against the complexity. It's not about a faster and everything. It's solving the. It's about to solve the complex and solving the specific problems. Okay, so the currently that supercomputers cannot handle the problems, so that can be solved by the quantum.
In
And
relevant to the speeds, the execution level of speeds, right?
Yeah, so execution level means, so sometimes the supercomputer cannot handle more complex problem. For example, in the encryptions. So in the SHA algorithm we have seen, right, some encryptions. So the current classic computers cannot use the encryption by prime numbers, but quantum can do. So those kind of problems too can be solved in the quantum. And so Rajanarayan, you are talking about any but specific point in the slide, or?
I think he may ask generally, sir.
Okay. So that's what. So we are keep exploring. So in that slide, I mentioned the milestone examples also. So 2019, what is the trial Sakamura processor? The Google tried with Sakamura processor with 53 qubits. They have done a trial with it's completing a task 20 to 200 seconds. So for the normal computer, it takes the 10,000 years. So they have did some trial, but in recently the Willow processor, the trial it's with the 105 qubits. So the statement is it's more than stable compared to the previous trial, 5 times longer than the previous trial. So that's what the improvement we can see. In 2019 we tried with 53, and 2025 we increased qubits and with the 105, and slowly it will be increased in some more days also. And this quantum, what is my understanding is this quantum, it's not used for as like a phone or laptop. So this quantum computing is morely used to solve the complex and large scale problems. It's not for the small problems. It's for the large scale problem, to solve the large scale. Large scale means the logistics, I'm telling you. So the logistics companies are my companies. I'm working in one railroad companies in US. So that railroad company, it's moving the container in all over the US, and also it's moving the some of the containers to other state, Canada and Mexican. So it's covering 3 countries of the business, and so they need to track everything. So each and every container. So for example, for one container, it has to be the application is has to be load the container into the train, and it reach the destination and unload the container from the train, and then we have to deliver the container to the particular customer of the place. So this is for about the one container we are talking. So just imagine how many containers daily it's processing. So in my application there are lakhs and 2 lakhs per day. Per day the lakhs are 2 lakhs events I'm seeing for the US one country. So if you think of the more large scale business, the quantum will help to solve the problem. So now the company having company can spend more money to the to track everything to deliver to the customer. So if quantum comes, maybe the company can company cost can reduce, company resource can reduce, and then company the moving items can be a faster. So it can just visualization. We are just visualizing about the relating with the current real world business.
Thank you, sir. Thank you, Ravi Shankar. You're giving a vast explanation about that quantum algorithms and then how the applications are implemented. And that I'm proud to be a resource person to become my student, alumni of our institution. Actually, during that intro sessions, I'm not able to continue that. One of our colleague, he was introducing yourself, but I'm happy on that. One of my student and alumni should be an resource person of the event, and he's well settled in EOS, Texas. Thank you, Ravi Shankar. Thank you so
Yeah,
much.
thank you. So
Uh,
actually, thank you for the opportunities. So even Rajshekhar talked to me about this. Even I was scared. So this is first time experience for me to explain in the meeting. So even I had a lot of meetings in my business, my office meetings I had, but this is the first time to explain to the outside peoples. Okay, so really I had a nice experience today.
Thank you, ma. Rajnarayan sir, can you propose a thanks message?
Sir, Ravi Shankar said, thank you very much for your lecture, which has taken for our last one hour. So we have gone through your slides. So we are enjoyed for 1 hour. So thank you so much for your. So if any queries, maybe you can share your ID with us. We'll just share with our candidates, so they may send you the queries and we can see in the future. Thank you so much, sir.
Yeah, thank you, Rajaran. Thank you, ma'am.
Sir, you may leave, sir. Thank you, sir.
Yeah, thank you.
The participants are requested to fill your attendance as well as the feedback form, which was displayed in the chat box. Please fill your attendance through that Google form. Thank you all.